Hey guys, this is Garrett here, your 118 tutor. So yeah, your finals here. I hope you all had a great semester and you're ready to go. Just to kind of give you guys some information on what it's going to look like. That's going to be similar to your exam 3 where it'll be online, um, of course. And it'll have 32 problems this time. Most of them are taken from the homework. And they shouldn't be crazy hard. Um, your problems from 5.3 to 7.3, so your unit 3, the last test material problems, are taken from that test that you just took. Um, the test will be open Friday and Saturday, April 17th and 18th. And so I'm just going to kind of give you guys a review of the things that you should know. For the final, I made this list here that you see right now, and it's kind of a encompassing, like if I were to like pack the course down into just a few bullet points from every unit, this is what it would be. So I will, at the end of this review, have a little slide with a bunch of review problems on it that I would go over and make sure you can do. And they're just homework problems, so you can go back to your homework, and those problems will best prepare you. I don't have access to your homework problems, so the problems I'm going to do in this review are from previous exam reviews. However, they will be over the same topics and should help you to be able to understand the material well enough that you are ready to take the test either way. Okay, so from Unit 1, you have sets. You need to have a good understanding of sets, subsets, all that. And then permutations, combinations. We're going to do some work with that here today, as well as the Tennessee method. Make sure you understand the union rule. The union rule is, the probability of A plus the probability of B minus the intersect of the two equals the union of the two. And that was what you used with the Venn diagrams a lot of times to find the union area. Okay? For Unit 2, this is all Test 2 material. Make sure you understand binomial probabilities. That's when we were the last using combinations to find like how many times it was likely for something to occur, right? Expected value, we do a little bit of that today. That's just an average. Standard deviation and z-score, we'll do that. And then make sure you understand the least squares line. I didn't have time to hit on that in this review, but it's basically like you need to know the equations for the slope, intercept, and for your R, your correlation coefficient. Unit 3 stuff, make sure you understand how to do Gauss-Jordan, know when it's complete, how to find an inverse of a matrix. You need to understand input-output models, when they're open and closed, maximum and minimum. Again, as I said, the Unit 3 material will be from the last test. Unit 4, you need to make sure you understand what makes a regular matrix, understand the equation VP equals V, how it ties into long-range probability versus term probability, and then Markov chains. I'll dive into that stuff super well. I know that's all new, and so I kind of talk a little bit more about that so that you can understand how that all works as well in this review. Okay? All right, so let's get going. Okay, so for combinations, permutations, multiplication rule, all of that falls under the umbrella of combinatorics. That's the long fancy name for what this stuff is called. There's a easy way for you to tell what type of way you need to go about solving each problem. So you're either going to be using the multiplication rule, you're going to be using permutations, or you're going to be using combinations. the way you determine what you're going to be using is based off of two things. Does it allow for repetition? Okay, first of all, multiplication is the only one that allows for repetition. The other two do not. The next thing you need to look at is it inclusive of different orders? Multiplication is. You can include all different orders of the same samples or events or outcomes. Permutation is also order inclusive. Combination is exclusive of orders, meaning that if you have 3 different observations, those will only be counted once despite the order that they're in. Okay, so you can use this kind of handy chart to tell, okay, am I going to use permutations, combinations, multiplication rule? I will say, going along with permutations and multiplication, those two are pretty interchangeable, meaning that you can use either of those two in most situations that you're not able to use combinations in because you want to be inclusive of orders. Okay, so for a problem involving combinatorics, we're going to look at this one. It says a bridge hand is made up of 13 cards from a standard deck of 52. What is the probability that a hand is chosen at random and has at least 3 aces? Okay, so there are 4 aces in a deck. We would choose 3 of them. Because we don't care what order the aces come in, we just know that we need to choose 3 of them. We know this is going to be a combination. Okay, so this is combinations all across the board. We don't care about orders. We just want these specific cards. Okay, so I have my 3 aces that I've chosen out of the 4 that there are. There are 52 cards in the deck, 4 of which are aces, meaning there's 48 cards that are not aces. So from those 48 cards, I need to choose 10 more. Okay. So that would give me a 13 card hand, 3 aces and 10 non-aces. Okay. And I would put that over the total, which is 52 cards, choose 13, right? So this is event that we want over the sample space. Okay. However, this says at least 3 aces need to be chosen. So that means we could also have 4 aces, which would look like this. 4 aces, choose 4. 48 other cards. This time we're just choosing 9. This is a combination as well. I gotta put that little C there, okay? All right, this is 1, so that cancels out, and they simplified it just down that far, so that's A. Another thing that'll be helpful to know, which could likely come up, is the Tennessee method, and that is a problem like this. So the letters banana are written on an index card and then shuffled thoroughly. What is the probability that when the cards are dealt out, they spell the word banana? Okay. So typically the Tennessee method you use when you want to find distinguishable ways to order letters. In this case, we're looking for a probability. So we know that there's only one way to spell banana, and that's going to be over the Tennessee method, which would be all the ways we could order the letters. So banana has 1, 2, 3, 4, 5, 6 letters in it. So that's the numerator of our little smaller fraction here in the denominator. There are 3 A's, there are 2 N's, and there's 1 B, okay? So we simplify that down, and that comes out to be 1 over 60. Okay, so that's A. All right. All right, this next problem deals with expected value. Expected value is very simple. It's just the average or the mean. So just think about it that way, okay? And that makes it a lot simpler than trying to complicate it at all. One of the easiest things you can do is just multiply across when you see one of these tables, add them up. That's the expected value.
Okay, so this is the value itself. This is the probability that the value will occur. In this case, the probabilities have to add up to 1, right? Because the event that's going to happen is one of these events. And so that means there's a 100% chance that at least one of them happens. So this adds up to 1. 0.1, 0.2, that's 0.3, 0.5, 0.7. So P1 equals 0.3. Okay. So now we just go ahead and multiply those all across. We get -5 times 0.1 is -0.5. -1 times 0.2 is -0.2. I could have done that in my head. I just didn't. 0.3 and 5 times 0.2 is 1. Okay. So now we add all those values up. 1 minus 0.5 minus 0.2 plus 0.3 is 0.6. Okay, so basically what that means is that is the value that you would expect to have. Notice it's not actually one of the events, right? There's no 0.6 in this x. X actually can't be 0.6, but that's saying like that's the average of x over all. Like if you ran this trial infinite times, that would be like the average x. Okay, the next thing you're going to want to know how to do is find a standard deviation. First thing you do is find the average. So we're given 5 numbers. The average of those 5 numbers would be the sum of all of them divided by 5. Okay. So 4 plus 2 plus 6 plus 9 plus 4 is 25 divided by 5. So x bar, the average is 5. The standard deviation equation is the sum of x minus x bar squared over n minus 1. You may have seen in like your statistics class that you just divide by n on the bottom normally and not n minus 1. That's typically for a population standard deviation. This is for a sample standard deviation. It's what we always use in this class. So always make sure you divide by n minus 1. A lot of times in your scientific calculator as well, you'll see a standard deviation depicted as sigma and another one depicted as s. If that's the case, you'll want to make sure you use this one that's depicted as s. It's for a sample, and that's what we're using in this class, for everything in this class. Okay, so going along with that, now we have our x bar. X is each one of these observations, so basically we'll do 4 minus 5 squared plus 2 minus 5 squared plus 6 minus 5 squared plus 9 minus 5 squared plus 4 minus 5 squared. Okay, that'll be our numerator. So let's do that real quick. We got -1 squared, we have -3 squared, 1 squared, 4 squared, and -1 squared. So this is 1 plus 9 plus 1 plus 16 plus 1. Okay, so 10, 11, 27, 28. Over n minus 1. N is the number of observations, which is 5. So over 4. 28 over 4 is 7. So remember, this is square root. Oop, let's see that. I'm going down too far. Okay, so let me just fold this up so you can see my work. Okay, sorry about that. And then S would be the square root of 7. Remember, that was the square root, which is A in this case, okay? And that's a standard deviation. All right, so when we're finding a standard deviation, typically we use that to compute a z-score. A z-score tells us the area to the left of an observation. So here's the mean, x bar. say we have an observation here. This is our x. It tells us that this area to the left in a percentage form. Okay, so it tells us how much stuff is under the curve to the left of that point. And that ends up being pretty useful. So the equation that we use is z equals x minus x bar, the observation minus the mean over the standard deviation. Okay, so in this case, we have an average of 3,500 hours. Sorry, there's a light bulb manufacturer. He's making bulbs. The average is 3,500. X bar equals 3,500. The standard deviation is 400. So assuming the normal distribution, what is the probability that it will last at least 4,000 hours? Okay, so the way that would look then is we'd have our little curve. The average here is 3,500. There's a standard deviation of 400, and we have an observation over here at 4,000. We're saying all this area, what's that equal to? Then, because it's at least 4,000 hours, the area we're actually looking for is right here. Okay, so we're going to have to take 1 and subtract out this because it gives us a percentage, right? And that would give us the area to the right. Okay, so 4,000 minus 3,500 divided by 400. So 500 divided by 400, 5 divided by 4, 1.25. That's our z-score. We plug that into the z-score table, which will be given on your test, and that one would give us a value of 0.8944. Remember, that is the area to the left. We need to find the area to the right, so we do 1 minus 0.8944 and get 0.1056. Okay, so 10.56% of light bulbs would last that long is basically what it's saying, that long or longer. All right, so we're back to minimums. If you need more help with these, go back and look at my exam 3 reviews, which has a more in-depth look at maximum and minimums. I'm just going to do a minimum problem here on this review because you've done both of those recently and they take quite a while, as you guys know. But hopefully this will be a good refresher. So we have our objective function y1 plus y2 plus y3. We're just looking for y1, okay? So what we'll do first is put all of these into a matrix. So we have these constraints that we normally, the ones that are just greater than 0, we normally just ignore, and we'll put in the other ones. So we have 3, y1, 0, y2, 4, y3, 16, and then 4, 3, 2. These are the coefficients to the constraints, and then you put the objective function in the bottom, okay? Which is just all ones in this case. All right, then we transpose that matrix. That gives us 3, 4, 1, 0, 3, 1, 4, 2, 1, 16, 12, 1. Okay? Make sure that's right. Yep. All right. Now we're going to insert the identity matrix into here. And we have to make this row negative, so don't forget that. Basically, you move this 1 to the same side of the equation as the 12 and 16, and that's what will make it negative. So our tableau will look like this. 3, 4, 0, 3, 4, 2, negative 16, negative 12, 1, 1, 1, 1, and lots of zeros. Okay, and then we have our ones here, so 1, 1, 1. Remember, this one moved from here to here, so now this is a 0 here, and that's why these are negative. Okay. Then we solve like normal. First, we'll find a pivot point, and then we will go through and solve this. So our pivot point, you go to the lowest negative, in this case, negative 16. Look at the column above it and find the smallest quotient. 1/4 You can't use a 0 or 1/3. 1/4 is smaller than 1/3, so we'll use this 4 as the pivot point. Okay. Now we're going to use that pivot point to change the other rows to 0. So I'm going to move this up so you guys can see it. Get a good crease on there. You can see it real well. All right, and then now that we have this 4, we can do a couple row operations. This is already 0 conveniently, so we don't have to do a row operation to row 2, but we're going to do one to row 1 and row 4. Okay, so the easiest way to change, this would be 3/4 times row 3. I'll do negative 3/4 times row 3 plus row 1. That'll cancel this 3 out. And then I'll do 4 row 3 plus row 4. Okay? So now my new tableau, row 2 and row 3 will be unchanged because we're not doing any row operations to row 2. And row 3 is the pivot row, so it will never change unless you pivot again. Okay, so first row 1, negative 3/4 times 4 is negative 3 plus 3 is 0. Negative 3/4 times 2 is negative 6/4 plus 4 is 2.5 or 5/2. Okay, 0, so that's still 1. This is still 0. This would now be negative 3/4, and this would still be 0. And negative 3/4 times 1 plus 1, so this would just be 1/4. Next, we'll look at the bottom row. 4 times 4 plus negative 16, that's 0. 2 times 4, 8, plus negative 12, negative 4. That means we're going to have to pivot again. Sorry. Sad, sad day. 0, 0, 4, 1, and this is now 4. Okay, so now we have to pivot again because we still have a negative. All right, so our new pivot point will go 1/2, 1/3, and I do not know, 0.25 divided by 5/2 is 0.1. Ooh. Well, that sucks. So this is our pivot point, 5/2. Okay. All right. So from here, got another sheet here because this problem's getting long. We're going to do that second pivot. I'm going to start with row 4 because if row 4 gets all positive, where there's no more negatives, I actually can finish in the case of a minimization because all my answers will be in row 4 and won't be affected by what's above them as long as everything in row 4 is positive. In the case of a maximization, you would have to do all rows. So I'll do, let's see, 5/2 to get that to equal 4. I'd have to multiply it by 8/5. So 8/5 row 1. So row 4 plus 8/5 row 1. It gives me 0, 0, 8/5, 0. This is my bottom row. Negative 3/4 times 8/5. Plus 4, 2.8 or 14/5. And that's still 1. And 1/4 times 8/5 plus 4. 22/5. Okay? So, that was fun. All right. So each one of these variables represents a row, right? We had our x1 and x2 and x3. This had 3 variables before we transposed it. no, actually, once we transposed it, it only had 2. Sorry, this is a slack variable. So this had 3 variables, then we transposed it, and now it only has 2 variables, and these are slack variables. This would be z, this would be our constant z is equal to. Okay, so in this case, it's asking, what is y1? Well, y1 is just equal to this value here. It's the bottom value in the column for slack variable 1. y2 would be the bottom value in the column for slack variable 2, y3, and the minimum in this case would be 22/5. However, all these values are subject to this 1. If this isn't a 1, if it's something greater, you have to divide the whole bottom row by 1. So the value in this case is 8/5, which actually is the answer. Believe it or not, it's kind of a wild problem. And a lot of people ask me, why do I use fractions? You don't have to use fractions when you're doing these row operations. I could have done like, 3 row 3 plus 4 row 1 or minus 4 row 1 and still got everything to zero out. You can do it that way if you want. I find it's easier to use fractions because I like to just have to do one step where I'm just multiplying one of the rows by something and adding it to the other row. It seems a little simpler to me, but you can do it whatever way you want. Okay, so this is the start of our Unit 4 stuff, and the first part of Unit 4 was to tell if a matrix is regular or not. The easiest thing you can do first to tell is look and make sure every row adds up to 1. Okay, so if every row doesn't add up to 1, then it's definitely not a regular matrix. The second thing you have to do, which is a little bit harder, is if every row does add up to 1, you have to make sure there are only positive non-zero entries in either the original matrix or its squared or cubed counterpart, okay? I would say you never, probably for this class at least, shouldn't have to take it past the third power. If you do, then it's probably just not a regular matrix. So what I mean by that is if you were to square this matrix, this 0 and this 0 would go away and there would be some other positive entry in both of those locations, meaning that it is a regular matrix, okay? Sometimes you'll get one that has several zeros. You'll square it, they go away, it's regular. Sometimes you'll square it and they won't go away, and you'll cube it and then they will, and that would still be regular, okay? So this next one I pulled in to kind of understand what we do with these regular matrices, and it has to do a lot with states, okay? So each matrix is kind of made up of states, or these transition matrices, and what those are basically is we're saying what is the likelihood that a state change will occur, okay? So in this case, we have a maze for rats with 4 compartments. The rat can move freely between compartment 1 and 2, and can also move freely, so I'll draw little arrows, between 3 and 4. But they can only go from 1 to 3, they can't go from 3 to 1, and they can only go from 2 to 4, they can't go from 4 to 2, okay? The location of the rat is checked every minute, and it's found that the rat is equally likely to stay where he is or move to any available adjacent compartment. What are the absorbing states of this Markov chain, okay? So we have 4 states. They can be in room 1, 2, 3, or 4, okay? If they're in 1, they're equally likely to stay there or move somewhere else. They can either move from 1 to 2 or from 1 to 3, but they can't move from 1 to 4 because there's no door. Okay, so that means they have a 0.33 chance of staying, moving to 2, moving to 3, and a 0 chance of moving to 4. Okay, 2 is the same thing. They can move to 1, they could move to 4, but they couldn't move to 3. So this is from 2 to 1, staying in 2, They can't move to 3, but they could go to 4. Okay. From 3, they can't move to 1. They can only move to 4. Or they could stay in 3. So can't move to 1. Also can't move to 2. 4, they could move to 3. They can't move to 2, but they could stay in 4. So 0, 0, 0.5, 0.5. Okay. All right. So this is what our matrix looks like for this problem. Okay. It has no absorbing states. All right. There is no room that once the rat enters, he cannot leave. That would be an absorbing state. Okay. So in this case, the answer is E. Okay, so now we have this problem kind of solved, but it is kind of important that you understand what an absorbing state is and how it works. So let's say that I have a 2-car garage. Wouldn't that be nice? I could park my car and stuff in 2 spaces, which is more than 1. Okay, so let's say I have space 1 or space 2. So let's say I'm parked in space 1. Okay, so rows make up the current state, columns make up the future state. Okay, so current state of the world is that I'm parked in space 1. Okay, if I'm parked in space 1 today, let's say that affects the likelihood of where I park when I get home tonight. Okay, so if I'm parked in space 1, the likelihood that I park in space 1 again is 0.2. Let's say I like to switch it up a lot. So if I'm parked in space 1, there's actually an 80% chance that I'll park in state 2 when I get home tonight, instead of parking in space 1 again. If I parked in parking space 2, then there is a 70% chance I'll park in space 1 when I get home. If I parked in space 2, there's a 30% chance that I'll stay in space 2 though, because space 2 is a little bit nicer. It's easier to get out of than space 1. Okay, so current state of the world is my row, future state is my column. Okay, the other thing with these transition matrices is sometimes you have something that is called an absorbing state. Okay, an absorbing state is a state that once you're in, you can't get out of. So for example, a 1 here and a 0 here, 0.7, 0.3. Okay, so this would be an absorbing state, right? Because let's say I park in space 1. There is a 100% chance that I park in space 1 again when I get home tonight. So instead of parking in space 2, I would park in space 1. And the thing is, now that I've parked in space 1, there's no chance I ever park in space 2 again, so I will never use that space in my garage. It will go completely unused. That's a lot of space for one man, so I just use space 1. Okay? All right. But what if it looked like this? What would that mean? Well, that would mean if I park in space 2, I can park in either space 1 or 2, but if I parked in space 1, there's a 100% chance that I'll park in space 2. So this wouldn't be an absorbing state, but this would. Because if I'm in this state, I cannot leave. I'll always stay in 1. If I'm in this state, I'll always leave, so it wouldn't be absorbing, right? This matrix would be an absorbing chain as well. Now, what makes an absorbing Markov chain is that it has one of these absorbing states. Not this one. That one's bleh. It has an absorbing state, and that state is accessible, meaning that in the column of the 1, there are other non-zero values. It's as simple as that, but basically what it means is that state can be accessed, right? There's a 70% chance that I'll get into state 1. If this was 0, then I could never get into state 1. I would be in state 2 forever if I had already started in state 2, right? So it wouldn't technically be an absorbing Markov chain. It would just have an absorbing state. Okay? All right. Okay, now we're going to employ some of that information that we've learned about transition matrices and absorbing states to talk about the long-range probability or equilibrium vector. It's the same thing. They use an equation that is v times p equals v, where v is our initial vector or future vector, and p is our transition matrix. Okay, so in this case, we are not given an initial vector, and that's because they want us to find a long-range probability or equilibrium vector. You will be given an initial vector if you are wanted to find a specific term probability. Okay, so this is basically okay. So what this is the current state of the world. Okay, when we're given term probabilities, we'll have, like, say, again, going to my parking spot example. Currently, Garrett is parked in space 1. That would mean it would be 1, 0. 100% chance I'm in space 1, 0% chance I'm in space 2. For more complicated things, like how many people live in single family versus multiple family housing, it'll be something like 20% live in single, 80% live in multiple, but it always adds up to 1. Okay? This side will be our future. Okay? And this right here is our transition. It tells us how it changes. So for a long-range probability, the transition matrix is the only thing that's given. Okay? We have, in this case, timed tests and not timed tests. Okay? We're told in this problem, an instructor is trying to decide whether the final exam should be timed or not. If it was timed last time, there's a 90% chance it'll be timed this time. Timed to timed again, 90%. If it was not timed last time, there is a 90% chance it won't be timed this time. So 90% it will not be. Okay, each row adds up to 1, so that's 0.1 and 0.1. Okay. Basically, if it was timed last time, there's a 10% chance it won't be timed. If it wasn't timed last time, there's a 10% chance it will be timed. That's what that means, okay? So now we'll multiply in our v's, and then we'll set them equal to v. So we have v1 times 0.9, 0.9 v1, plus v2 times 0.1, 0.1 v2 equals v1. Then we have 0.1 v1 plus 0.9 v2 equals v2. Okay, so we have those two equations that we've pulled out by multiplying that all together and everything. You add in a third equation, v1 plus v2. You just always add this one in. v1 plus v2 equals 1. Or if there's 3 v's, because it was a 3 by 3 transition matrix, v1 plus v2 plus v3 equals 1. Always add that in. Always throw one of these out. Doesn't matter which one, just throw one out. But make sure you leave this one in. Okay. Now we get the v on the same side of the equation. If you had more of these equations, you'd get all the v's over. Leave the one on this side, though. Okay. So 0.9 v1 minus v1 is negative 0.1 v1 plus 0.1 v2 equals 0. And we also have v1 plus v2 equals 1. Now we're going to use Gauss-Jordan to solve this. Negative 0.1, 0.1, 0, 1, 1, 1. Okay, first thing I'm going to do is change this value to a 1. I'm going to multiply the whole row by 10. Okay, that gives me negative 1. This gives me 1. Okay, we're just going to put little x's there. Okay. Now, I want this would be positive, so I'm going to make that positive and make that one negative. That's like multiplying the row by negative 1. That's what I did there. Okay. I want this to be 0, so I'm going to do row 2 minus row 1. Makes my new row 2. Now I have 1, negative 1, 0. 1 minus 1 is 0. 1 minus negative 1 is 2. And 1 minus 0 is 1. Okay. Now I need this value to be a 1, so I'm going to divide the bottom row by 2. That gives me 1, -1, 0, 0, 1, 1/2. Okay, and now I'm going to add this row 1 plus row 2 to get this to be a 0. And that gives me, sorry, you're going to follow my arrows, know where I'm working at. 1, 0, 1/2, and 0, 1, 1/2. Okay, so my equilibrium vector in this case is 1/2, 1/2. Okay, 50-50 chance. So we're looking at D here. That's the long range average as to what percentage of exams are timed. Okay, so we're going to use our little information that we learned about transition matrices again on this problem. In this case, though, we are trying to find specific term changes. So a medical researcher is studying the risk of heart attack in men. She first divides men into 3 weight categories: thin, normal, and overweight. Okay? By studying the male ancestors, sons, and grandsons of these men, the researcher comes up with a transition matrix for 1 generation. Okay? Find the probability that a man who is overweight has a thin grandson. That's 2 generations. From a man to his grandson, right? Because it could be man, son, grandson, 2. Okay? The first column, thin, middle, normal, third is overweight. Okay? All right. So if I want to know 2 generations, but I'm only given a transition matrix that represents the change over 1 generation, I need to square that matrix. Okay? When I'm squaring a matrix, I'm just multiplying it by itself: 0.3, 0.5, 0.2, 0.2, 0.6, 0.2, 0.3, 0.3, that's 0.4. Okay? Right. So remember, rows by columns. Okay. We know we need a probability that a man who is overweight has a grandson that is thin. Okay. That would be this value, the bottom left value, right? Because it's from overweight to thin. Okay. Because we know we only need to find 1 value, we don't have to multiply every single value. We just have to do this last row by this first column, because that would give us that value. So 0.3 times 0.3 plus 0.3 times 0.2 plus 0.4 times 0.3. Okay, that gives us 0.3. 0.27. Okay. So that's how transitions work over multiple periods. You'll notice, as I said, it's really important to know that rows make up current state, columns make up future state. And that will help you distinguish how the change occurs over time.
Okay, and so as I said, these are some problems that you can review on your homework to help you know exactly what's going to be on the test and be able to be prepared for anything else. This is specifically from your professor, what she said she would review for the test. So I would go over and look at these problems. You just pause the screen and screenshot it, whatever, and go take a look at those problems.